2465, number of distinct averages. This is a new problem dropped recently in this week's contest, so I'm hoping that I'm one of the first people to approach this problem and provide a valid solution. Okay, so you are given a zero-indexed integer array nums of even length. As long as nums is not empty, you must repetitively find the minimum number of nums and remove it, find the maximum number of nums and remove it, calculate the average of the two removed numbers. We know how to do averages. Return the number of distinct averages calculated using the above process. Note that when there's a tie for maximum and minimum number, any number can be removed. All right, so it's a pretty approachable problem. Let's look at these nums here. Now, in the first round, you're going to remove the minimum number, which is 0, and the maximum number, which is 5. And the average is 2.5, right? And then you'll be left with this array here. Then you look at the minimum and the maximum again, which is 1 and 4. 1 and 4, 2.5. Remove those again. Then we look at 4 and 3, 3.5. And since we got 2.5 twice and 3.5 once, we have in total 2 distinct numbers among the averages. Okay, so I think the solution to this problem is a n log n time complexity, and I guess it would be n time space complexity. Okay, so O of n log n time, O of n space. So where does this O n log n time come from? Well, the easiest thing to do here, because we have to constantly remove maxes and mins, is find the minimum in an iteration and the corresponding maximum. Now, we could do that in n squared time if every single time we removed an element, we looked for the min and looked for the max. But it will probably be more efficient if we first just sort the array and then pull from the left and pull from the right. Meaning, if we had this array here, right, we'd sort it first and end up with 0, 1, 3, 4, 4, 5. And then we could have some sort of pointer that points here and a pointer that points here. And on the first iteration, we know this number and this number. And then we move our left pointer to the right and our right pointer to the left. And it'll always have the invariant where the left pointer is pointing at the minimum and the right pointer is pointing at the maximum, because we sorted the array first, right? So if we didn't sort the array and we tried to look for the maximum and the minimum of every iteration of finding averages, that would have n squared runtime complexity, which is obviously much worse in worst case runtime. Okay, so let's go ahead and do that. So the first thing we'll do is we'll sort nums. And I guess we can do in place sort here instead of adding an additional array. And we'll have a left pointer equals 0 and a right pointer equals length of nums minus 1. And we'll go ahead and put that on one line just so that it looks better. Now when we look at each thing, how do we know when we're done? Well, we'll have left here, right here, and left here, and right here, and left here, and right here. So once left passes right, you're done with this problem, right? Like you process 1 in 100. The second the iteration where left is greater than right, you have the case where you ran out of numbers to process, right? So while left is less than or equal to right, I say less than or equal because you could have a odd length. Oh no, num's length is even. Okay, so you can't have an odd length, so that's fine. So while left is greater, less than right. Ugh. So L plus equal. So after the iteration's done, right, we're gonna have L added 1 to L and minus 1 to R. Okay. So we've sorted nums. Now, to find the average, right, the average is L plus R, or sorry, nums at L plus nums at R, right, nums at the left pointer plus num at the right pointer divided by 2. Right, we're just doing very simple, elementary grade math. And then now we need to think about how we're going to account for the number of distinct elements, right? Well, I think the most intuitive thing to use here would be a set of averages. Now this is where the n times space complexity comes in, right? Because we need n additional space for this average set. Because the cool invariant of a set, right, is that if you had A equals a set, or I'll just show you in here. Right, the cool thing about a set is that every element is unique. And if you try to add the same element twice, it will just maintain the same state as prior, right? So if I had A as a set, average, and I added, imagine we had the average 2.5, and then we saw the average 3.5, and then we saw the average 2.5 again. When I print average, notice that it's just 2.5 and 3.5, right? So if you attempt to add a duplicate element, the state of the set won't change. So that means that the number of distinct elements is just the length of this set, right? Because if we keep adding averages, all the duplicates will be discarded. Therefore, the length of the set in the end will be the number of distinct elements, right? Because an invariant of a set is that it has all unique elements. So then instead of just taking the average, we can just add this average to the set and go through this process. And then when we're done, we just return the length of average. All right, I'll submit that. And there you go, faster than 100% of solutions. That's because there's probably not that many people that have submitted answers to this question yet. And then if we wanted to just shorten it a little bit, not for any additional, save and runtime, but just to have the solution look cool and very Pythonic, I guess. A lot of these things can be on the same line. Of course, this is more for the aesthetic rather than any extra runtime improvement. So it may be the case that this needs to be over here. Oh, I messed this up already. All right, let's submit that again. And there you go. There's a 3-line solution. All right, have a good day. Thank you, everybody.